All right. Any questions before we get started? And I apologize, you can tell I'm a little sick this week. So I didn't do any grading this weekend, admittedly. I was just dying. But check your grades, make sure that they're updated. So I still need to grade your energy lab. Hopefully I'll do that soon. But other than that, check your grades, make sure they're accurate. I saw some people have been emailing me extra credit, so I'll try to update that as well so you can get a better idea of where you stand. And so like I said, don't forget for extra credit, just email me if you've registered. Or I know some people have to meet with an advisor first before they register. Just let me know that. I'm in progress. I'm going to meet with my advisor. We're going to register, and then you'll get those bonus points. And then again, December 2nd at 1 p.m., I still need to verify the room, but we'll have our talk. And like I said, it will also be recorded as well. So 2 opportunities for extra credit points to really help you at the end. And so, of course, this is our last week of lab, I guess. And so this is our lab final this week. So on Wednesday, and so it's pretty simple, some multiple choice questions of matching, some flame tests. What else is on there? One of those like unknown identification, so you don't have to do all the tests. I know people were joking about trying to turn that litmus paper blue. Instead, it'll tell you whether it turned blue or not, and then you just have to interpret the results based off of course, what the lab says. So bring all your labs. You can use them. Like I said, I'll get those energy ones back to you, hopefully by Wednesday, and anything else that you turned in. And you can bug me, too. And I'm also kind of behind on posting notes, so I owe you guys probably notes. But you know, if you go to my YouTube channel, you can find all the videos anyways, even if I don't post direct links. So all videos are uploaded immediately, but I'll try to get those notes updated. All right, I gave myself a really bad paper cut, and it's like bleeding, so I'm going to take care of that. Yeah. Sorry. All right, sorry about that. All right, now we're ready for our final chapter, unless there are any questions. So our last chapter is acids and bases. I think it should be a pretty fun last chapter. So acids, you probably have tasted some acids in your time, although now that I said that, that came out wrong. Not thinking of drugs. So acids, you know, I'm drinking some lemonade, so that would be acidic. You know, you got your lemon, and so you know that they taste sour. You know, oranges, those are also all our citrus fruits, of course, natural acids. And so we've seen this in lab where acids have the ability to dissolve metals. So we'll put on there our HCl plus magnesium. We watch that dissolve. And then, of course, acids neutralize bases. So you saw that most recently in your titration reaction. So NaOH plus our vinegar. And so here are some examples. And if you have a blue litmus paper, it changes to red. And so we have our strong acid, hydrochloric acid. This is a weak acid, acetic acid or vinegar. And some more common acids. So hydrochloric acid, this is going to be the primary component of your stomach acid. And so, of course, if you vomit or something, right, all that stomach acid is very corrosive for your teeth, so that's not good. Or, you know, if you were to be bulimic, then, of course, that's why that people with bulimia tend to start getting, like, their teeth eroding and having teeth issues because of how acidic your stomach acid is. And so the other thing is, and this is kind of an aside, is like if your stomach acid is so acidic, you know, does it really matter what you eat so much? So there's a lot of controversy about alkaline diets. Are you guys familiar with that? And so some people say, like, if you do an alkaline diet, and so alkaline, this means it's going to be basic. So you're going to be consuming foods greater than 7 for your pH, maybe drinking like that higher pH water. Have you seen like the higher pH water and stuff like that, like the pH 9 water? And well, there's a lot of controversy of whether that actually works, since of course the first thing it's going to do is hit your stomach acid and, you know, be neutralized there. So still some controversy about this interesting topic. And so sulfuric acid, this is what's used in fertilizer production, a lot of explosives too, and then this is going to be in your battery. So nitric acid, that's also used in fertilizers and explosive manufacturing. So acetic acid, you probably know that from vinegar. So also used in other manufacturing or food preservation. So citric acid, this is just the isolated then acid that's found in lemons and limes. So we also have the powder form of this in lab, and then it's also used to make candy. And carbonic acid, so carbonic acid, right, that's what happens when we have carbon dioxide dissolving in water. And so that's present in carbonated beverages, or if we're talking about like ocean acidity and that sort of reaction, we'd be interested in carbonic acid. So hydrofluoric acid, again, we mentioned this is pretty dangerous. If you're working with hydrofluoric acid, you have to have the antidote. And so it's mainly used in glass frosting and etching, or metal cleaning, or like making silicon chips. And so, of course, the important thing about HF is you cannot store in glass. So it has to be in plastic. So that's different from all the other acids. So all the other acids can be safely stored in glass. They come in a glass container, but not HF. It will eat through that glass. And then phosphoric acid. So it's also used in fertilizer manufacturing, and then also found in like your sodas. That's beverage preservation. So there's phosphoric acid, and of course carbonic acid in soda. And so the other type of acid that we've looked at, or can look at in this class, are organic acids. And so these carboxylic acids all have this COOH group. And let's just draw that out. So that's going to be C, one double bond to an O, the other one OH. And then it doesn't matter what it's attached to here. And then we mentioned, so this is called the acidic proton. And so that means this is the one that's going to be coming on and off in solution. So if we have our reaction, and we'll just use water right now as our base. So water comes along. It has those two lone pairs of electrons, so that means it's primed to attack. And so this two electrons here, it's going to see this hydrogen, so it's going to give those electrons to hydrogen. So now hydrogen doesn't need these two electrons, so it's going to kick those back to our carboxylic acid. And then the final result of that will be, formally, we make H plus or hydronium. So sometimes you see that abbreviated as just H plus. And then you would also make your base, so your salt there. And so again, why this is so stable is then this is resonance stabilized. And well, what do we mean by resonance stabilized? All this means is we can draw another form of it. We can move the electrons around. So this is where we started. But we could make a double bond here. So now carbon has 5 bonds. So we have to kick these two up on that oxygen. So if we write our new structure, that gives us something like this. And right, again, resonance just means that the true form is kind of the combination of both of those structures. And so you might also see it abbreviated something like that. And a negative charge there showing that you have a negative charge that's spread out among these two oxygens and delocalized across there. So that's what makes those organic acids stable and defines an organic acid. And so, you know, if you go on and take either 105 with me or, you know, do like med or wherever you take OChem later, then you'll see this carboxylic acid group probably pop up again. And, you know, it could be attached to a phenyl. It could be attached to any sort of thing. Just as long as you see that, you know you have some sort of acid. So now looking at bases, and so you probably don't want to taste bases, but if you've ever, I don't know if people's parents still like wash their mouth out with soap. I don't know if that's still a thing. But so if you ever got your mouth washed out with soap, then you know that it tastes bitter, or maybe you just get like some shampoo in your mouth or something. And so it often feels slippery too. And so it has the ability to, of course, neutralize acids, and it changes red litmus paper blue. And so many of your cleaning products are bases. So Drano, I believe, is essentially sodium hydroxide, just diluted. And then other ones, so here we have ammonia. There's our other base, or a sodium hypochlorite, or bleach. Hypochlorite, bleach, so all those are bases. And so common bases, so we've seen sodium hydroxide, so this is used in manufacturing processes, also soap. Have you guys made soap before? From like sodium hydroxide pellets. So it's pretty fun. If you do take 105, I believe our first lab is soap making, and we'll still do that, even though it's online, so I'll probably do like instructions for home cooking. But super fun, and you can actually make soap with either sodium or potassium hydroxide, and that just does the saponification reaction and converts your oils. So soap is made from like some combination of oils, so it could be like olive oil, coconut oil, almond oil, something, and then that just does the saponification and turns it into soap. And so you're probably also familiar with sodium bicarbonate. So we have this in lab as our neutralizer, otherwise known as baking soda, also known as an antacid. And sodium carbonate is another base, so also used as a water softener. And then ammonia, again, a lot of people use this as a cleaner, and of course it's also used in fertilizer manufacturing, so that's a big use for ammonia is its fertilizer. And of course ammonia is also used for explosives. And so now let's look at this hydronium ion, and I kind of alluded to this earlier. And so all this is saying, and so even if you have, you know, we always write this disassociation, like HCl disassociates to H plus chloride. And all we want to emphasize is even though we use this abbreviation, you know, all the time, and you see it all the time everywhere, in reality, you cannot just have H plus ions in solution. And so basically this is because they're so reactive that they don't exist. And so what actually happens, we have our HCl, and then so as it's disassociating, right, oxygen is going to come, just like we saw with the carboxylic acid, our lone pair on oxygen from water can go ahead and grab that H, and so then we make our chloride ion and then hydronium. So this is what actually exists in solution, but again, like we've seen, chemists just simplify it by using H plus. And so this is just the proper reaction of what's going on. And again, all that is saying is as soon as you have your naked proton here, it would not exist and just be readily swept up by that oxygen to form hydronium. And so note the charge on this structure. So oxygen has the plus charge there from its formal charge.
Can you draw that for the aluminum hydroxide? Because the book had it and I couldn't like visualize where the electrons were.
I'm trying to find. Because aluminum hydroxide is actually a funny one.
I was trying to draw it and I couldn't figure out like where it was taking them.
I was hoping I had the right visual, but I think it was from my other class. So I think it has something like aluminum, and there are like hydroxides everywhere attached to it. Is that correct?
3, yeah.
And then usually with these aluminum species is they're considered formally basic, or they'll make like a basic solution. And that's because, so you have this aluminum hydroxide, and you have all these waters floating around. And so what's going to happen is this hydroxide tends to grab one of these hydrogens and then make this aluminum water adduct here. Oops. And then that itself would leave you with hydroxide in solution then and make the solution basic. All right, so now let's look at the definitions of acids and bases. And so we'll start with the broadest. And so Arrhenius theory, this is just the most basic theory. And so we can look at, you know, HCl or nitric acid. And so these follow this pattern, and that by the Arrhenius definition, acids produce H plus ions in solution. And again, we see this for our simple acids, so it disassociates, making our H plus and chloride in solution. So that makes it an acid by this Arrhenius definition. And so by the Arrhenius theory, bases produce hydroxide ions. So we can most easily see that with like sodium hydroxide, potassium hydroxide, or magnesium hydroxide, right? All those dissociate to form hydroxide ions in solution. And so in these simple acid-base reactions then, with our Arrhenius definition, and we've kind of seen this before with our double displacement, but if we just do HCl plus sodium hydroxide, we know that the partners swap around to give us water and then our corresponding salt there. And so we've seen that, so acid plus base gives us salt and water. I'll just put on a side there, so this is our double displacement and also neutralization reaction. And so what's the problem with this Arrhenius theory? So unfortunately, it's just too narrow of a definition. So for example, it doesn't tell us why ammonia dissolves in water to form a basic solution, even though it doesn't contain hydroxide ions, right? So that doesn't tell us what happens. It's not telling us it splits. Where's the hydroxide here? So there's something more to this picture. And then it also doesn't explain how, for example, sodium carbonate or sodium oxide dissolve in water to form basic solutions. Again, even though they don't contain hydroxide ions, so we have some issue here. And it also doesn't explain, so why does carbon dioxide dissolve in water to form acidic solutions, even though, again, there's no H+ ions. So what's going on here? And so next they came up with the Bronsted-Lowry acid-base theory. And so now it's looking at what happens in the chemical reaction. And so now we're looking at a reaction that transfers a proton from one molecule to another, regardless of whether it occurs in aqueous solution or if there's hydroxide ions present. And so, of course, all acid-base reactions that fit the Arrhenius definition also fit the Bronsted-Lowry. And so with our new Bronsted-Lowry definition, an acid is defined as an H+ ion donor. And so if the acid is the donor, that must mean that our base is the H+ ion acceptor. And so this is our general form of our Bronsted-Lowry acid-base reaction. So we have some sort of acidic HA acid plus our base, gives us our new conjugate base, which was formerly the acid, right? And now it's just stripped of its proton, giving us our anion, so that's our new base. And then our new conjugate acid is going to have the proton on it and be positively charged, and that would be our conjugate acid. And so now if we look at this definition, so going off our Bronsted-Lowry definition, so looking at this, so again, water is now acting as a base. And so we should probably mention, if you haven't realized already, so water is pretty cool in that it can act as both an acid or a base. We'll see that happen depending on the situation. And so in this situation, we have HCl, so this seems to be our proton source. We know that water can go ahead and deprotonate that and then form our hydronium. And so in this case, water is our base since it's accepting that proton. Just don't write H plus jumping over there, so that would be inappropriate. So all your action should always initiate from the electron. And so now this is our new conjugate acid. Since we added a proton to it. So our base, now, if it was formerly our base, we should have added a proton. And now this is our new conjugate base. And again, comparing it to the acid that it came from, so it should be a difference of a proton. And so now this finally explains ammonia. And so let's look at, well, what's going on with ammonia. And this is where our Lewis dot structures really help us out. So if we draw our Lewis dot structure for ammonia, we have our nitrogen, right, 3 hydrogens, and then our 1 lone pair up at the top here. And so now it's in solution with some water. And so in solution, so we have this nitrogen here. It sees this proton over here, so it's going to go ahead and attack. Let me change colors. So now it's going to attack that hydrogen. So the electrons in that bond then go back to our oxygen. And now, so that gives us ammonia. So plus charge on our nitrogen, plus our hydroxide. And so that, I'm just showing all the electrons on there so it's clear. And so now looking at this and analyzing the reaction, well, what happened? Well, I can see that ammonia is accepting this hydrogen. So that makes ammonia our base. And so now this explains, well, yes, ammonia is a base, and this is how it produces hydroxide ions in solution. And so that means water in this case was acting as our proton source, so it's our acid. Now after the reaction, so now our ammonium is our conjugate acid. And so we gained a proton. So again, that tells us it's our conjugate acid. Now comparatively, so our former acid, right, lost its proton. So now we made our conjugate base. Again, our base is missing a proton. So any questions on this part up here? And so again, the nice thing about this is we can just see the equilibrium. And of course, you could reform this. So if this was a weak acid, right, you have reversibility. So this is for weak acids and bases. And so that also explains, so if you remember in lab where I just told you that ammonia equals ammonium hydroxide, so now we can really explain why. So we draw out this reaction, and let's draw the full structure. So we have ammonium hydroxide. And so they're sitting there in solution. And so in solution, if this is a positive charge, our oxygen has this negative charge. So it's going to want to attack. So it's going to go ahead and attack that proton there. So it's going to deprotonate our ammonium. Those electrons are going to return back to nitrogen. And that's how we get our ammonia in solution. And then, of course, that would just make some water there. And so you'll also see this conjugate acid-base pairs. I think your lab from last week had a really nice chart of acid-base pairs, so I would definitely look at that, study that, use that on your exam, whatever. And so like we're seeing, the original base becomes our conjugate acid, and so it would be our acid in the reverse reactions. We could kind of flip this again backwards and forth if we're talking about weak acids or weak bases, right? Those have the equilibrium. And then our original acid becomes our conjugate base in the reverse process. And so each reactant and product then, it becomes is called a conjugate pair. And so you want to be able to recognize conjugate pairs. And they should only differ by a proton, either adding a proton, in this case, so we have our ammonia and ammonium conjugate acid-base pair. So again, just adding or removing a hydrogen. Or we have our water and hydroxide acid-base pair, just removing or adding a hydrogen. And so something to watch out for is when you have a difference of like 2 hydrogens, it would try to fool you. So this would be not a conjugate acid-base pair. And so something that is not would be hydronium and hydroxide. And so this is often put on exams and tests to confuse students, and it's something like identify the, conjugate acid-base pairs. And this looks nice because they're both related to water, but the big problem here is that we have 3 hydrogens versus 1. And so they're not acid-base pairs. They both have to go through water. And so let's just add correct acid-base pairs. And so that means hydronium and water are an acid-base pair because they differ by a hydrogen. And then water and hydroxide are the acid-base pair because they differ by a hydrogen. So just watch out for that. Those will be tricky scenarios or things that could trip you up there. And so again, just looking at this reaction, we've looked at it. So our ammonia was the base, then it became our conjugate acid of ammonium, and we have our base pair. Then we have our water and our hydroxide, so that's our other conjugate acid base pair. And so again, a base will accept the proton and become the acid. The acid will donate the proton and become the base. All right, so take a few minutes and look at these 2 reactions. So we have sulfuric acid plus water gives us our hydrogen sulfate ion plus hydronium, and then our carbonic acid here plus, well, that's not carbonic acid, I guess hydrogen carbonate plus water gives our carbonic acid plus hydroxide. So identify who's the acid, who's the base, and we'll go over it. Basically, so it's like right there in the middle of pH 7 anyways, and so that's what makes water really cool, is that, yeah, it's an acid or a base. So in this first one, so is this H2SO4 our sulfuric acid, is this our acid or our base here? So acid, and then so if this is the acid, what's water? Base. And then so what's this species now? Conjugate base. And then what's hydronium? Excellent. And so now let's look at the second one. Oops. Oh. So what's this species? So base, excellent. So this is a base. What's our water? Acid. And then what's H2CO3? So our conjugate acid. And so this is carbonic acid. And plus, so we made hydroxide. And so what's our hydroxide? Excellent. Any questions on that? You'll seem pretty good on that section. Oh. Let's go back, and I at least want to mention what the last acid definition was. So we did these main two, and these are the main ones that we care about. But the last one here, I didn't want to just neglect it. But this is called the Lewis definition. So you have Lewis acids or bases. And so that's going to be, an acid is something that accepts or needs an electron pair. And bases donate an electron pair. And so one of the good examples of this is they're called frustrated Lewis pairs, but they're also acids and bases. And so the best example of this, let me make some space, is you have like boron trifluoride, so BF3. So this is going to be your acid, because we can tell boron is electron deficient. So we mentioned that that's one of those odd things about boron. So it only has 6 electrons total. Obviously it wants 8 like everybody else. And so it can make this frustrated Lewis pair with like ammonia or another nitrogen-containing compound. And so in this case, right, nitrogen is donating both of its lone pairs to BF3. And so this makes BF3 our acid then, in this case, since it's accepting an electron pair. And then bases, so we already, define ammonia as a base through our other definition, but now we can see, well, it also obeys this Lewis acid-base theory since it's donating its electron pairs. And so again, this is most expansive. So we probably won't talk too much about this Lewis acid-base definition, but it will certainly crop up if you continue in chemistry. And so now let's look at strong acid versus weak acid and base. And I think we've talked about this before, but again, now we're officially hitting the chapter so we can again formally look at it. And so like we've seen or mentioned, a strong acid, all this means is it is a strong electrolyte, so it's going to completely disassociate in solution. And so again, we see that with our HCl, with our nitric, hydrobromic, hydroiodic, not hydrofluoric though, so that's the audio. And then the weak acid, again, has nothing to do with how dangerous it is, but just whether it is ionized. And so with a weak acid, again, we only have that partial ionization, and the key point is that there is equilibrium, and so it can reform in solution. And this will come up more in lecture as we look at more topics. And so I'll show HF. Again, HF. And then that makes those fluoride ions, those salts. Fluoride, of course, would be basic, since they can go ahead and reform HF. And so same thing with the base. So again, a strong base just means it completely disassociates, like we've seen with sodium hydroxide, potassium hydroxide, versus a weak base where you only have, again, a small percentage ionized in solution. And again, you have that equilibrium back and forth action. So now let's look at some trends. And so let's look at this first one. So it says the stronger an acid is at donating a proton, the weaker the conjugate base is at accepting a proton. And so this kind of has to do with what we were saying about strong versus weak acids. And so if we think about this, what it's really saying, so if we again look at our HCl case, so the stronger an acid is at donating a proton, so that also means, right, disassociating, giving it away. So the stronger that is, that means that the weaker the conjugate base is. So which one's our conjugate base in our HCl here? Yeah, so it'd be the chloride. So this is your new base. So it lost the proton. And so now this is saying, so the weaker the conjugate base is at accepting a proton. And this makes sense with what we just said about the strong acid is completely disassociated. And so all this is saying we have a strong acid, and because HCl is so strong, basically chloride is a very weak base, or such a bad base that it doesn't go in reverse. So again, chloride cannot come up. So what you're thinking about is, can it do this? And nope, it cannot. So that would not happen. It does not reform HCl. And so meanwhile, again, the reverse, or comparing HF. So now stronger acid, well now HF, we said it's a weaker acid, and so that means that maybe the conjugate base can accept the proton. And that is what happens in this case, so that your fluoride ion salts can go ahead, and of course this would be hydronium, and they would pluck it off the water, but they will go ahead and reform HF. And so other general trends, so the higher the oxidation number, the stronger the oxy acid. And so like sulfuric acid is stronger than sulfurous acid, so the lower oxygen. Nitric acid is stronger than nitrous acid. That's all that means right there. And so the other thing you can kind of notice, so cations tend to be acids. So a cation will be a stronger acid than a neutral molecule. Neutral molecule, stronger acid than an anion, and so anions tend to be more bases. And trend in base strength, the opposite. And so this is a handy chart. I can print one if people want one while you are quizzing. And so I like this because it also helps us with our next section when we talk about like our salts, acidic or basic. And so if we look up here, so these are our 7 strong acids. And so we know they're strong. Obviously they're up at the top, but a couple of things that it also tells us here is that undergoes complete acid ionization of water. Okay, so I know that they're going to fully disassociate these top 7 here. And then the other key thing that we care about, so across from our acid, right, is a conjugate base salt. And so now if you look, So now it's opposite, so we have increasing acid strength. So these are the strongest acids, but now these are going to be the weakest bases. And so if we look at that and we think back to what this little saying was saying, the stronger the acid, the weaker the conjugate base. Well, all our strong acids then, their conjugate bases, right, do not undergo base ionization in water. So all of these, anytime you see a salt, right, they can't reionize or anything. So these are all going to be neutral salts as well. So that's also what it's implying. And so again, I'm just kind of re-emphasizing what's going on. So our nitric acid going to disassociate and make our nitrate, right, our conjugate base here. And then it's saying, okay, it's not going to undergo base ionization in water, so it's not going to be able to pluck anything off of that water and reform our nitric acid. And so again, this would mean like sodium nitrate salts then. So that would be neutral from the nitrate. So you would dissolve it in water. And I think you did some of this in lab with like the pH testing and the salts. Well, that's kind of what you were going for is this salt solution acidic, basic, neutral? And so that has to do with its acid that it came from. And so again, all that's saying is our nitrate is floating around, and this negative charge cannot go and attack a hydrogen. That's all that's saying. And so now looking at our next one, so our next one is hydronium, and of course the base is water. Obviously it's down at the bottom, pretty weak base. And then we can just compare. So next is our hydrogen sulfate anion. So notice, right, sulfuric acid was a strong acid for the first dissociation, and then now at the second, it becomes a weaker acid, so there's an equilibrium associated with the process of that. And of course, its corresponding base, so sulfate. And so now sulfate could go ahead and reform the hydrogen sulfate ion in solution. So you could go back and forth from sulfate to hydrogen sulfate, but then you can't reform sulfuric from this hydrogen sulfate. And so you can just kind of keep reading for yourself. So we have phosphoric acid. Again, the first one is just that first dissociation. There's HF, and of course fluoride. Nitrous has our nitrite ion. So now nitrite could form nitrous acid in solution. So same thing with acetate. So did you notice something? So I think you tested sodium acetate in lab. Do you remember it having a pH by any chance? Or I was curious. I guess someone's going to pull out their notes. What do we get for that? What did the pH paper tell you when you have it? Do you have the pH? 7. I was hoping for like a little bit higher, like 8 or 9. But this is cool, so let's look at what it would be doing in solution. So you have your acetate. So there's acetate. And then again, what it's going to do in water, so let's draw this out better. And so now it's acetate. It has a bunch of electrons over here, and so those electrons can go and attack our proton. And so now it's going to reform our acetic acid, and then it would leave us with hydroxide ions in solution. So then continuing down, so you can see carbonic acid, again, first dissociation there. So hydrogen sulfide is also an acid. There's our ammonium, hydrogen cyanide, hydrogen carbonate, so from our carbonic acid. And then water now, so water, conjugate base hydroxide. And now down at the bottom, these last ones, so these do not undergo acid ionization in water, so they can't split or anything. So ethanol, right, doesn't lose that H or anything, so that's not an acidic proton. Ammonia also doesn't lose H or anything. And then we have methane. And then, so these undergo complete base ionization in water, so they're not going to be reforming anything. So sulfides, ethoxides, amides, hydrides, methides, so they're not going to be reforming methane or anything in solution. So that's all that means there at the bottom. Questions on this chart? So this chart's pretty important, and we'll revisit it too in our other sections as we kind of look at it and how to use it. And so now there are other ways to, again, say, is it strong, is it weak? And so do you remember the K equilibrium expression roughly? Do you remember that from like our other chapters now? And so let's look at what goes on. So again, we have HCl, disassociates, or let's do the more general form. So we have our HA, of course, disassociates to form H plus A minus. And so then we can set up our Ka expression. And so all this is, so Ka, if you kind of remember from previously, remember it was products over reactants. Does that sound like vaguely familiar? And you put it to like the powers and stuff. We like briefly talked about it, so it's, I can see why people don't remember. But then for acids, so that means, so our products are going to be H plus and our conjugate base there over our HA, so whatever concentration of acid. And so that now all this is saying is we have this expression, and of course for our acids, it's going to lie all the way to the right, so all the way to our product side. And so if our Ka is greater than 1, and so we're seeing, okay, that means we're going to have more products than reactants, then that's telling us, again, that it's a strong acid. And so nearly 100% ionization of acid molecules occurs in water. And so again, that match up with our expression there. And so those are your 6 strong acids. And so then for a weak acid, again, looking at that general, the most general Ka expression, so products over reactants. So now if we're saying it's less than 1, then we're going to have more reactants, right? And so that means in this weak acid case that we're going to have, it's going to favor the reactant side and of course not produce as many products. And again, we've mentioned some weak acids, so this is just listing some more. So acetic, carbonic, or formic. And so acid or base strength is also measured by determining the equilibrium constant of a substance's reaction with water. And so what we need to at least understand is roughly how to read this. And so the farther the equilibrium position lies towards the products, the stronger the acid or the base. So if we compare this acid, so hypochloric acid, so 1.1 times 10 to the negative 2, versus cyanic acid, 1.9 times 10 to the negative 10. So we're looking at which one's less negative. So this one has a greater value. So we can tell that this is the stronger acid. Blah, blah, blah. So that's our formal expression again for Ka. And again, the larger the Ka value, the stronger the acid. So this is a nice chart here. So this is some organic acids and other weak acids. So you have chlorous acid, and again, they're just arranged. So the strongest acid is on top. We'll look at what pKa is in a second. And so again, you can just appreciate right now the Ka. So as we go down here, they get weaker. So here's acetic acid. So that's 10 to the negative 5 range. Hydrocyanic acid, that was 10 to the negative 10. And there's phenol. So that's an acid there. And weak, so also to the negative 10. And so like we've seen with water, so water can either be an acid or a base, and so that means it's amphoteric. And so that's, again, super cool about water. So hopefully you appreciate water a lot more. And so therefore there have to be some ions present. And so this was also pretty cool too when they were trying to figure out the pH scale and they're analyzing water. And so water also does this cool thing called auto-ionization. And so all that means is that water can ionize itself. And I'm just drawing out what's shown here. So of course the top is just kind of the most simplest, but doesn't really give you the chemical perspective of what's going on. So it's just kind of showing water splitting, which is appropriate to think of what's going on, at least the end result. But you should really think about what's going on in the molecular level. So what's truly going on, two water molecules are staring at each other, and then one of them can go ahead and attack. And of course that gives you our hydronium ion then. And then of course leaving us with hydroxide for the other one. And so this means that all aqueous solutions must contain both H+ ions and hydroxide ions in solution. And so it was, again, really cool. They're first studying water, and so part of the standard that they found, and again, how we got to our pH scale, we're kind of building that. But they found that the concentrations of hydronium and hydroxide are equal in water, at least. So this is at 25 degrees Celsius. And they found that the concentrations were 1 times 10 to the negative 7 molarity. And, oh.
Is the auto-ionization, is that the same thing as the
Amphoteric?
Yeah.
They're related. So amphoteric just means it can be an acid or a base. And I'm trying to think. There's got to be other amphoteric substances. I'm trying to ask Google. Like apparently some amino acids can also be amphoteric. So yeah, all that means is it's an acid or a base, but it is very closely related to why this is and how it forms these two ions. And so then how we got to our pH scale is, so then they came up with this ion product of water constant, Kw. And so all Kw is it's the concentration of hydronium times hydroxide ions. And so they found a couple of things. So they found that the product of hydronium and hydroxide concentrations is always the same. And so that answer is 1 times 10 to the negative 14. And so this is super useful. So whatever you need to do, so Kw is always that. Kw is always whatever your concentration of hydronium times hydroxide is. And so you get hydronium times hydroxide gives you Kw. And so this means if we measure one of the concentrations, we can always calculate the other. And so, of course, if our H plus ions increase in solution, then hydroxide ions must decrease so that the product stays constant. And so again, that's key, that Kw is always constant. And so all aqueous solutions contain both hydronium and hydroxide ions. So neutral solutions then have equal amounts of hydronium and hydroxide. And so if it's truly neutral, so that means pH 7, then it would have concentrations equal to 1 times 10 to the negative 7 molarity. And so if you have an acidic solution, it's going to have a larger hydronium. And so that means it's anything greater than 1 times 10 to the negative 7. Hydroxide, of course, will be less than that. And then you can imagine, so basic solutions would be the opposite. So they have larger hydroxide. And so your hydroxide concentration should be greater than that 1 times 10 to the negative 7. All right, start with this, and then I feel like as soon as you do this, I'll reveal the easier way to do it, perhaps. So see if you can determine acidic, basic, or neutral. So looking at A here, so it says hydronium concentration, or H plus, is 7.5 times 10 to the negative 5th molarity. So is that greater than or less than our 10 to the negative 7? So greater, so if it's greater, is it acidic, basic, neutral? So acidic. And then what about B? So B, it says our hydronium concentration, 1.5 times 10 to the negative 9 molarity. So basic, so it has less than at 1 times 10 to the negative 7. And then C, so what is that? Acidic, basic, neutral? Oh, neutral. And so now we're getting to the pH scale. And so a couple of things. So the easiest thing, so we have our pH, and so we saw pH in lab, we use pH paper. Now we just need to get a scale, and what the heck is pH? So pH is the negative log of the H plus concentrations in solution, and so the negative sign just counts for that, the negative exponent. And so if let's just plug in one of these values. And so I will give a warning. So I think the hardest part of this chapter is just entering stuff into the calculator. So whatever calculator you want to use on the exam, you should use it and practice with it and make sure you're in like the correct log base 10 and all that good stuff. Especially there's like weird finance calculators that are not in base 10 or something. So that's my word of warning. And so let's just plug in one of these from above. So we said the pH is the negative log of our H plus concentration. So if I want to plug in A here, so 7.5 times 10 to the negative 5th. And so that gives us our pH. And then what you'll kind of notice is the exponent should roughly give you the pH. So this was negative 5, so I was expecting something around 5. And so it's closer to 4, but still good. So 4.12 for our pH. And then so let's do the next one. So negative log 1.5 times 10 to the negative 9. And so again, just looking at that, I'm expecting somewhere around 9 for the pH. And so the calculator spits out 8.82 for our pH. And so of course this one would give you 7 if you were to plug that in. And so let's look at our pH scale now. And so notice, so this is our H plus concentration and pH. And so our pH scale goes from 0 to 14. And so we've seen that 7 is in the middle, so that's our neutral. So anything below 7 is going to be considered acidic. Anything greater than 7 is considered basic. And then so the other thing is, so now this explains why our pH scale is 0 to 14. So it all goes back to this Kw constant. And so notice that has a concentration of 14. So that is what is driving your scale there. And so now just looking back at this chart, we can put some things in context. So we mentioned again, your stomach acid is super acidic. So lemons, limes, so those also aren't too good for your teeth to have them, bathing in lime and lemon juice. Soft drinks, so of course soft drinks aren't also good for your teeth because they have pretty low pHs. And then so fruits tend to also be acidic. Wine, so some people are concerned about wine as well, again with your teeth. All that can lead to acid erosion. And then apples, peaches, cherries, so those are also acidic. So beer is slightly acidic. Rainwater, tends to be around like 5.6 or could even be lower with acid rain. Human blood, so remember human blood is a buffer and it's kept at a pretty tight pH, so you have a bunch of reactions going on in your body, and so you want to keep it right around there, of 7.3 to 7.4. So egg whites are going to be slightly basic. And then has anyone taken like milk of magnesia for upset stomach? No. Well, that's 10.5 if you've ever used it or maybe seen it at the stores. And then household ammonia, so that's pretty up there, so 10 to 11. And then your sodium hydroxide, that's going to be at 14.
Where's coffee at?
That's a good, let's ask Google. It's got to be like slightly acidic. I like this Henry's House of Coffee, apparently. There's somewhere around like the 4 to 5 range. Yeah, if you get really bored, you can always sneak some pH strips from lab, you know. Curiosity, man. All right, so let's look at these two. So calculate the pH, and then tell me if it's acidic or basic. And then see if you can guess what to do with B. So let's start with A at least. So that one was straightforward. So we had our pH is equal to the negative log of this. So we just have to plug that in. So negative log of 1.8 times 10 to the negative 4th. So did we get 3.74 for the first pH? I see a lot of nods. And I have to look at the sig fig rules again, but I remember something that like if you have 2 sig figs and you have like an extra one that you report, but honestly I have to look back into those rules to look at the math behind them. But. And then what do we do for B? There are 2 different ways to do B. Anybody? Don't want to do natural log. Yeah, so that's one way to do it. And so let's explain why that works. And so it all goes back to that KW constant thing. And so we'll find that pH is really circular, but you have this sort of thing. So that's one way to do it. And this is perhaps probably the more tedious way, and I'm just going to do it to show y'all. So you could solve for H plus concentration, that would be one way. So 1 times 10 to the negative 14 for our Kw, divided by hydroxide. Then we get this number, so now negative log of that. So that gives us 12.11. But then, so you had said, well, what if we just put this into our calculator? So negative log of 1.3 times 10 to the negative 2. And so this is correct in that it gives us, so this gives us POH. And so we're about there, but not. And so I'll reveal the formula now. So POH is equal to the negative log of our OH concentration. So we get that. So that's our POH is equal to 1.89 or so. And then so you had said subtract from 14, so that's absolutely correct. And so that goes to this relationship, which is derived from our KW relationship. But this is probably easier just for everyone's sanity math-wise. So whatever you need to, wherever you need to write this, so pH plus POH equals 14. So everybody have that written? People know their site. Yeah, for our purposes, we'll always assume. And the variation is very small anyways from this constant. So yeah, we'll just always assume it's 14. And then so going back to this problem, so we calculate the POH, and then we can do 14 minus that, and that also gives us the pH. All right, so for the interest of time, we'll have to stop here. So we'll pick up tomorrow, revisit POH again, so we feel good about that. Or not tomorrow, but Wednesday. And then again, just make sure your calculators function and you're getting the correct answers out. If you're having calculator issues, I'm more than happy to help y'all or lend you the calculator so I can get like lab calculators. You can practice on those and feel good about that. So let's go ahead and take our 10-minute break. I have homework too up at the front, so you can grab that. And then we'll do our quiz in 10 minutes when we return. I will go ahead and stop this recording.